Have you ever wondered, is there another object aside from a mass on a spring that undergoes simple harmonic motion? That is there something else that you regularly come in contact with that exhibits a force which is proportional to its displacement? Is there something that, given what you now know from a previous video about simple harmonic motion and springs, that you can leverage to understand? Well, that object is a pendulum, and a simple pendulum is going to be the subject of today's intuition video. What's going on, everybody? It's High Peak Education, and I'd like to introduce this video by comparing a pendulum to a mass on a spring, and this mass on a spring is on a frictionless surface. And the idea is that we're just going to compare the energies. So we're going to see that there's a really nice analogy between a spring that's in simple harmonic motion and a simple pendulum. Now let me explain what I mean briefly by a simple pendulum. That simple pendulum has a mass on the end of a string, and let's assume the string is extremely light. In other words, we're going to ignore the weight of the string. So we're going to assume that this ball, by the way, is basically almost like a point mass at some length from the axis of rotation, which typically will be mounted to some stationary ceiling or something like that. Okay, and the idea is that we're going to not worry about the rotational inertia of this mass. If you did, that would make it a physical pendulum. And also, if the string was not light, that would make it more of a physical pendulum as well. And with this pendulum, what also is going to make it simple is we're going to assume no friction, no damping, no air resistance, and for that matter, we're also, for reasons that I'll explain later, going to assume that the initial displacement angle is quite small, usually 15 degrees or less in practice. Okay. So let's go ahead and take a look at this pendulum. Notice that it has a weight force on it. You would expect that when it's on Earth. Now, the G here is the gravitation constant if we're near the surface of the Earth. That's approximately 9.8 meters per second squared in SI units. Well, you can imagine that when the pendulum is pulled backward and it's going to make this arc, that it's going to undergo a displacement. But as it undergoes a displacement, it has a force on it, and that force is going to be the component of the weight that goes down towards equilibrium, which will actually be mg sine theta, and theta is going to be the angle with reference to vertical of this pendulum. Okay, so you could imagine it at some point here we're essentially forming a right triangle at some time, and that angle theta is the angle of deflection from straight down. Alright, so let's examine, when we pull this mass back, the pendulum simultaneously will pull back. I think we're going to be only in terms of elastic potential energy for this spring, but when the pendulum goes backward, it also has potential energy. But that potential energy is gravitational potential energy, namely energy stored up in the gravity field. So, the restoring force is going to be the weight for this pendulum, whereas the restoring force for this spring was the Hooke's law spring force. That's actually going to create slightly different behavior for the pendulum as opposed to the spring, but we'll discuss that. Note that the spring had its maximum speed through the equilibrium position. That is to say, the kinetic energy was maximum moving through x equal to 0, and we'd expect the same behavior for the pendulum. We expect the gravitational potential energy to become kinetic energy, and then via inertia, the kinetic energy will move up to the other side, and this should be symmetric and continue on forever in the absence of any damping or friction or air resistance or things like that. So, let's examine. Notice all the energy is only in potential energy, that is, the total energy equals the potential energy, and notice that we have simple harmonic motion of the simple pendulum and the spring. Now notice on the pendulum that the weight is always straight downward, and there's going to be a component of the weight that's parallel to the string, and that's the mg cosine theta component. Whereas the mg sine theta component, again, theta is the angle with respect to vertical, that component is largest at the greatest deflection, but then it's zero as we move through equilibrium. But notice when spring is maximally compressed or elongated, which is to say when the pendulum is at either of the fully swung positions, the potential energy is maximum and equal to the total energy. The kinetic energy is maximum and equal to the total energy through equilibrium. But notice that the potential energy goes down as the kinetic energy goes up, and vice versa. The sum of kinetic plus potential energy will be the total energy, and this is just the conservation of mechanical energy. Alright, so I think we understand in general what's going on with the pendulum. I'd like to be a little more quantitative in the next experiment, where we can set the angle, we can set the mass, we can set the length of the string, all kinds of things. So we'll examine the pendulum. We'll also be taking a look at the pendulum's frequency and period, which are quite important things. So now what I have here is a mass on a pendulum string. Let's assume this is an ideal pendulum with no friction. The gravity is currently set to the gravity constant of Earth, which is what we'd expect, but we can actually control that. We can also control the amount of friction. I won't be changing that in this video. We can also control the mass, that is this point mass. We can control the initial angle. Here are some angle measures in degrees. And then we can control the length of the string. What we can do is we can also measure the time of a period, and I'm also going to allow what's called a period trace. You'll see the time that the pendulum takes to go back, one full swing forward, and then back to like one full oscillation. Okay? So a period trace will start from equilibrium. We'll go left, right, and then back, left, and then that'll be one full period. Okay, so in other words, the object will be moving back to the left where it originally started. Okay, so the idea is we want to investigate the properties of this simple pendulum. So, first of all, we want to investigate, does the simple pendulum depend upon the amplitude? Remember, the mass and the spring did not depend upon the amplitude because we got a larger force, thus a larger acceleration, when we had a larger displacement. So is that still the case in the simple harmonic motion here? We think intuitively it might be the case, but let's investigate. So let's try two experiments. Let's try a 5-degree deflection, and let's see if we can measure the period. Okay, notice that this is what we mean by the period trace there. So I need to start it when... So it's right about 1 second. I think I did it quite right. Notice that the period is about 1 second. So you see, looks like a quarter second, half second, quarter second. A quarter second, half second, quarter second. So hopefully you see that in the motion of this pendulum. Okay? So that's for 5 degrees. But let's see if we could reproduce the same results for, say, a larger angle. Now, for reasons I'll explain here momentarily, we want to keep the angle less than 15 degrees. So what I'm going to do is I'm going to stop this and then go up to 15 degrees. That's sort of the maximum I want to go to. And then let's see if we can reproduce that same business with the period. So I need to get ready on the stopwatch here. Ah, looks like it's pretty darn close to 1 second. Let me try one more time. I'll wait for it. Ah, pretty close to 1 second. I mean, I'm 0.03 of a second off, but hopefully you'll forgive me. But you get the idea. I think it's about 1 second. That's the period of this pendulum. Okay? Now, by the way, this is a very well-known fact. There's actually a legend about this by Galilei, who was sitting in a cathedral in the 1600s, and he saw a very, very large lantern hung from the ceiling, and when the wind would blow, the pendulum, no matter its amplitude, would have about the same period. And again, he sort of investigated this and he wrote some things about this. Okay, so let's investigate two other things, maybe even three. Let's start from top to bottom. Let's go length, then mass, then gravity. So let's start off with the length. So what do you think? Do you think that this pendulum should depend upon its length? Pause the video if you need to and have a think about it. So welcome back, and hopefully you've had a think that if I increase the length of the pendulum, it turns out that I think we're going to swing through a larger arc, and I think that the gravity component won't be downward with as much of a component, and I think that what we're going to have is we're going to have a longer period, okay? And that's because the larger the length, what we're going to have is a larger arc to swing through. So let's see what happens when we double the length to half a meter. And again, let's go back to 5 degrees. And again, hopefully you can see it looks like the period is longer, the frequency is less. Let me see if I can wait for the next. Okay, looks like it's about 1.45 seconds or so. Now it turns out that's actually pretty close, because previously it was about 1 second. Believe it or not, it should be square root of 2 times the original period. Now that's not necessarily obvious until you start working out the mathematics. The square root of 2 is about 1.44, so I was only off by about 100th of a second. That's pretty good, I'll pat myself on the back. But you get the idea that it is indeed longer. Let's see if that square root of 2 works in that. Let's pause. And let's now go to a length of 1 meter. Now a length of 1 meter, given that that's 4 times the original length of the first original experiment, this should take twice as long for the period, so half the frequency. So let's go up to 5 degrees, and let's go ahead and watch. Okay, so hopefully this is about 2 seconds. Let's wait for it. Okay, so pretty close to 2 seconds. I'm only about 0.2 of a second off. Okay. Now, let's go ahead and see if I can get the same result for a 15-degree swing. So let's go up here to 15 degrees. Okay, so hopefully this takes 2 seconds. Let's see if I can measure. Okay, that's pretty darn close to 2 seconds. Hopefully you see that this is indeed what we have. Now, by the way, notice that independent of amplitude is the period or frequency of the pendulum. But notice, certainly dependent upon length. So as long as you have 2 pendula which are the same length, they should give the same period. Let's see if we can verify this. So here I have a length 1 pendulum, and let's see if I can add an additional one in. Here I have another length pendulum, okay? And I'm going to try to start these things at different moments, but I'm going to try to see if they have the same period. So let's pull this one back, and let's choose a different angle. Let's do 8 degrees. Okay. And by the way, let me go ahead and, because I haven't discussed it yet, let me reset this and let me set both of these to a mass of 0.75 kilograms. Okay. So let's go 8 degrees for this one. And then let's set this one to, I don't know, let's go 4 degrees. Why not? And let's see if these are the same time for a period. Let's go. Okay, hopefully you can see that. Hopefully you can see that. Let's go ahead and make their initial displacements even larger. Let's make one of these about 7 degrees. So let me stop. This one's about, and then let me pause, by the way. Let's go 7 degrees, and then let's have this one go about 15 degrees. So about twice. We can only be accurate up to about 1 degree. In fact, let's just go 14 degrees. Okay, you see that their period is unchanged from the 1 meter period that we just discussed. But, again, the blue one swings further than the red one. So mass 1 has a larger arc length swept out than mass 2. So what that means is mass 1 has a larger angular acceleration than mass 2. But it turns out that even though mass 1 has a larger angular acceleration and a larger torque, because essentially it's rotating about this axis, it is going to displace a larger angle. And so again, the time is the same for these simple pendula. Okay? That being the plural of pendulum. Okay, let's take away that first object. Let's go back to that sort of basis experiment of 1/4 of a meter. And then now, let's increase the mass. Notice now we have a bigger object. So 1.50 kilograms, about twice the mass. Now what do you think should happen? Previously with a spring, when you had the mass, when you would increase the mass, the period was longer and the frequency was less. Yeah, so what do you think is going to happen this time? Pause the video, talk to your neighbors, talk to your cat or dog, whoever's around, and try to think about this and then come back. So, welcome back, and hopefully you realize that it actually should be the same period. Now, indeed, the weight force will be larger because we have a larger mass, but think about this. A larger weight, but also a larger inertia. So the net effect of those masses goes away. So let's first do our 5 degrees. Okay, let's see if we can show this to be 1 second. Oh, I missed it. Let's try this again. Okay, so it's pretty close to 1 second. The period is actually unchanged for a larger mass. And that's because, unlike a spring, the spring has the Hooke's law spring force restoring it back towards equilibrium. The pendulum has the weight itself. So if you increase the mass, you have more inertia, not just more weight, bringing it back towards equilibrium. So there we go. Let's see if we can verify this with the 1 meter length. So remember, this should be 2 seconds. Let's go 5 degrees. This is going to be easier to time on the stopwatch. Okay, so it's close to 2 seconds, and again, there's really no change with the mass, okay? The only difference in the timing is just user error based upon myself. I'm trying to do this live. Okay, so hopefully that makes sense. And notice, even if you go 15 degrees, you still should have the same behavior. Let's try. Pretty close to 2 seconds. Okay, so you get the idea. So unlike a spring, a pendulum is independent of the mass on the bob. Okay, so this is sometimes called the bob, or the point mass on the end. Okay, so now let's change back to our original 1/4 of a meter, and let's change back to our original mass of 0.75 kilograms. But now let's change the gravity acceleration. Let's go up to the moon. So let's imagine somehow we could take this pendulum, go up to the moon, perform an experiment. What do you think is going to happen now to the period? Remember, the period here for 0.25 meters, I think has usually been about 1 second. Talk to your neighbor, talk to your cat, talk to whoever's around you, and pause the video, have a think about it. Okay, now this time I think the period is going to be, let's see, so if the gravity force is less, I think the period should be longer because there's a smaller restoring force. Okay? So if the gravity is less, I think the restoring force is less, so the period should be longer. Let's see if we can verify that with a 5-degree angle. And go. And indeed, the period is longer. Turns out the acceleration due to gravity on the moon is about 1/6 of that which it is on Earth. That's why you can jump much higher on the moon. You've seen the astronauts bounding around, hopefully, in videos before, and so on and so forth. Well, that's the restoring force of a pendulum would also be less on the moon. So I timed it. It's about 2.46. And that's because, since we have about 1/6 the gravity acceleration on the moon, the period should be square root of 6 times larger period on the moon as opposed to on Earth. Now, by the way, square root of 6, we know the square root of 4 is about 2, so it's a little bit more than 2 times. So 2.46 seems reasonable. Let's go ahead and try 15 degrees. So let's go up here to 15 degrees. Okay. Let's try to measure. Okay, so again, about the same. So that's what we expected. And let's stop. Let's go 1 meter length. So instead of 2 seconds, it should be 2 seconds times square root of 6. So just for fun, let's go 10 degrees. Okay. I'll have to wait till it completes one oscillation, then I'm going to try to go for another period trace to make the period measurement. Let's go now. Okay, so it's about 5 seconds. So 5 seconds, I hope, is about 2 seconds times about square root of 6. Okay, so hopefully you can verify that. So let's try 2 times the square root of 6. And again, 1/6 the gravity acceleration on the moon. It's just approximate. Hey, it's pretty close to 5 seconds. I was off by about 1/10 of a second, but again, that's user error. And keep in mind, this 6 is also rounded off. It's not exact for the moon. Okay, so there we go. Sounds good. What would the case be if we were on Jupiter? Now, Jupiter has a larger gravity acceleration than that of Earth. So lots of gravity. Again, we're ignoring friction the whole time. If we go 10 degrees, I think it should be higher frequency in a shorter period than that of Earth. Let's do play. And indeed it is. Let's see if I can measure the period. It won't be long for it to come back. So it's less than 2 seconds. Okay? So that's because the gravity acceleration of Jupiter is less. Okay, now I want you to see a simple pendulum in one more way with sort of one more experiment. And this time I'm going to be plotting different kinds of, I'm going to be plotting different kinds of variables as a function of time. So I want you to see the sinusoidal behavior of those variables as a function of time. So what I have shown here is a simple pendulum, and we can plot various things versus time. And we're going to see those variables plot out as a function of time. We can choose either the elongation. Now, by the way, the elongation is basically how far we are elongated from the equilibrium position along this red arc length. We're going to plot the velocity as a function of time, the acceleration as a function of time, the force, and even the energy. Okay? So that's the basic idea. We can set the mass, gravity acceleration, the length, the amplitude in degrees, and we can also slow the motion down. So let's see what this looks like for a 5-meter pendulum. Notice that for a 5-meter pendulum, the period is 4.49 seconds. You can see that the position is just sinusoidal with time. Now, when I say sinusoidal, what I really mean is it's sort of a pure cosine function, just like what we did with the spring, but notice that the maximum value here is 0.873 meters. And that's because the length of this red arc from equilibrium, this curved distance, is 0.873 meters. Okay, so that's why we start off here. cosine starts at its maximum value. We want the phase shift to be 0 if possible. So this is exactly what we see. We see that this is a cosine function with the amplitude of the maximum elongation. By the way, notice that the units of the elongation could be meters along an arc length. But a lot of times when people write down this time-dependent function, they write it as theta as a function of t. Now don't get confused. Theta max is often expressed in degrees, but when you get to the cosine omega t, what's inside of cosine omega t is actually in radians. That's because omega has units of radians per second in traditional angular frequency or angular velocity units. So don't get confused on that. Okay, what if we look at the velocity? Now, first of all, the velocity is going to be shown here as a vector, but what do you think the velocity's time-dependent graph is going to look like? Well, I think it's going to start off at 0, then it's going to be positive, well, actually it's going to go to the left, and then it's going to be maximum value, at least in terms of speed, then it's going to go back to the right. So I think it's going to be sort of like a negative sine function, because it starts at 0, when it moves through equilibrium it's going its maximum speed, but then it starts going back to the right. So look at that velocity vector. Do you see the velocity vector is a tangential velocity? It's tangent to the path. The speed is 0 when the pendulum is maximally at the ends and stationary. The object has the greatest velocity through the equilibrium position. And when I say maximum, I mean maximum speed. So the velocity is either negative when it's moving left or positive when moving to the right. The period is definitely the same because we haven't changed anything about the pendulum. Let's take a look at the acceleration. Now, what do you think about the acceleration? Okay, it's going to sort of be like the opposite, the negative of the position function. Why is that? Because the position function was positive to start, starts to the right, but the acceleration should be negative, it should be to the left. But it also should be a negative cosine function. So the acceleration is tangential acceleration in meters per second squared. So that's like a negative cosine function. So notice the acceleration is maximum when the pendulum is at its maximum displacement. And when I say maximum, I mean maximum magnitude. The acceleration is to the right when the pendulum is displaced to the left. And the acceleration is to the left when the pendulum is displaced to the right. So notice it's like a negative cosine function. Okay. Now let's take a look at the force. Well, the force should just be a tangential force. So basically we just take this acceleration and multiply by some sort of mass to get this in newtons as opposed to meters per second squared. So if we take 1 kilogram times this force, in fact, let's go ahead and change it to 2 kilograms. Let's change this to 2 kilograms. And just for fun, we know that shouldn't change the period, but what about the acceleration and the force? So when we go to force, we should see, yeah, twice that acceleration. So 3.42 as opposed to 1.71. Now, by the way, it's not necessarily perfect. There's some round off error there, but you get the idea. And notice that, again, the tangential force is exactly the same vector except scaled up by the mass compared to the tangential acceleration. Okay, so I think we understand that. Let's move on. And then now let's look at the energy. So the energy should be what we were showing before. Notice it's all potential energy at first. So that's up here. But then when we get to moving through equilibrium, it's all kinetic energy. And these should cycle through as basically, with respect to potential energy, it's going to be like a cosine function squared. Whereas the kinetic energy is going to be like a sine function squared. Okay? And notice that, remember, each energy is positive and the total energy stays constant. And you'll see that this bar graph is going to oscillate around. So there we have it. Notice that we have oscillating potential and kinetic energy. Let's slow the motion. Notice that when the object is moving towards equilibrium, the potential energy is becoming kinetic energy. Now it should be all kinetic energy through equilibrium. when the object is moving back up to the angular displaced maximum point, it becoming all potential energy, and then of course the oscillation just continues. So this is what we mean by a simple pendulum. Now, by the way, one thing to briefly mention here. The reason it's a simple pendulum is because the angle is very small. It turns out, we've said before earlier in this video, that the restoring force towards equilibrium goes like mg sine theta. By the way, you have to work out the mathematics and the signs, that is the SIGNS, positive or negative, or either positive or negative depending upon how you set up the diagram and so on. But anyway, the magnitude is mg sine theta. It turns out that if you put that into Newton's second law for this thing, now, by the way, you could do Newton's second law in a linear sense, in terms of a tangential force, or you could do Newton's second law in terms of an angular acceleration and a torque. And you could define this as a point mass with a point mass rotational inertia. Either way will get you to the same answer. But the problem is, you'll end up with a second time derivative equal to a function of theta that's a sine theta function. It turns out if you try to solve that, you need things like hypergeometric functions and all kinds of mathematics that I don't really very deeply understand. So what we often do is we say that sine theta is approximately theta for very small angles. Let's explain why we say that. Notice this is like a sine function, is it not? Notice that sine theta equaling theta, imagine this graph was flipped on its head. So the graph would just go like this. Sine theta equaling theta means the line y equals theta is very, very similar to sine of theta, very close to the origin. That's what we sometimes also called a first order Taylor series approximation. Because if you write out the Taylor series expansion, which is actually a Maclaurin series because we're centering around 0, but if you write out the Maclaurin series expansion for the sine theta function, it turns out that you get like theta minus theta over 3 factorial plus, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus dot dot dot. So you get an alternating series, and if we just take the first term, to a first order approximation, the sine function is indeed like a linear function. So that's what we're assuming. And if you make that assumption, not only is the equation much easier to solve, but the form of it looks exactly like that of a spring, and so it basically behaves in terms of simple harmonic motion. If we change the amplitude to something dramatically different, say 45 degrees, well here it's 20 degrees. It's not going to quite be simple harmonic motion anymore. I'm not sure if you can really see that. And back to here, which we had before, recall that this 1 meter length for, say, 10 degrees should give us a period of about, let's see, what was that? On Earth, it gave us a period of about 2 seconds. So let's wait for the period trace to clear, and then I'll try to time it. Okay, so it's about 2 seconds. Let's see what happens if we go to a very large angle. So it's out of the screen, but let's do 45 degrees. So I don't think it's a simple pendulum anymore. So let's see if we can estimate this. Okay, it's a little bit longer than 2. Turns out that, it's not going to behave exactly as a simple pendulum anymore. Okay? This might be programmed behind the scenes to behave like a simple pendulum, but again, it's not going to perfectly obey that mathematics anymore. So that is still an important assumption if you're going to analyze this as a simple harmonic oscillator. Thank you very much for watching this video. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks, and I look forward to seeing you in the next video. Thank you for watching High Peak Education.